Okay, welcome back guys. Good evening everyone. Now in this class we are going to discuss about general pathology. In today's class we are just about the topics that are related to the general physiology. In this class we'll be discussing about the topics related to the general pathology. Now in the series of general pathology lectures we have already completed our basic understanding basic topics. That's the cell injury, different types of cell injury, reversible cell injury, irreversible cell. After irreversible cell injury, we have also discussed about something like different types of cell death like necrosis, apoptosis, the pathways of apoptosis, necroptosis, pyroptosis. All these topics were already discussed in the previous videos. Okay, now in this class, in this video, we'll be continuing the topic of a cellular injury. Okay, now in the tomorrow's class, we'll be starting with the inflammation, acute inflammation, chronic inflammation. Inflammation, the second chapter will be discussed in the next class. Now, in this class, we'll be discussing the miscellaneous topics, which are also highly important for your exam. The topics which we'll be discussing in today's class are cellular aging, why we age, how cellular aging will occur, what is the cause that cellular division will decrease, what makes a cell to get old. Okay, the cellular aging, the first topic we are going to discuss, and the second topic which we'll be discussing is the different types of calcifications. Okay, like metastatic calcification and dystrophic calcification with examples, and at the end will be mainly concentrating on the questions which were asked in the previous exams. Okay, all the questions are compiled in one single place, and all those things will be discussed. Okay, now having said that, now let's discuss our topic, cellular aging. Okay, cellular aging. Okay, now my question to you is, why does cellular aging will occur? Okay, why cellular aging will occur? What, see, we all know cells are having a capability to divide. Older cells will be replaced with the newer cells. If that happens continuously, we shouldn't age. Okay, now why aging will occur? We all going to become old because the capacity of the cells to divide is going to decrease. For example, think like this: if you are having an ability to completely, continuously replace the old cells, you will never become old. You are going to be immortal. Okay. Now, why do we age? That topic will be discussed here right now. Okay, cellular aging. Now, our cells are going to be continuously encountering two types of problems. One thing is, the first important point is free radical damage. Free radical damage. Okay, so what exactly are these free radicals and what they will do, we'll discuss next. Now the second most important cause, this is the most important cause of cellular aging, and the second most important cause is shortening of telomeres. Okay, shortening of the telomeres is the other cause. Now first let's see what exactly are these telomeres and what exactly is the shortening of telomeres have to do with the cellular aging. Okay, it's very simple. Now I'm asking you, we all have cells, right? Every one of us who are listening this class, we all have cells, all the different types of cells. Okay, germ cells, epithelial cells, all different kinds of cells. Now inside a cell there is something called as a nucleus. Inside the nucleus, what do we have? We have chromosomes. Okay, we have something called as chromosomes, in which you are having the DNA material on which genes are there, and all the time these chromosomes are dividing. That will further continue as a cell division. Okay, first chromosomes will divide, later cells will divide. Now I hope you already know this from your basics. The end parts of a chromosome are called as the telomeres. Telomeres. Okay, the end parts are called as the telomeres. Now, important point is here. See here, inside a chromosome, what do we have? Inside the chromosome, we are having the nuclear, the DNA material. Okay, here imagine like here are the DNA. Let's try to understand like this. Okay, here is a DNA material. See, but in the telomeres, whatever the DNA sequence, whatever is there, it's nothing but a continuous units of PT, PTA, triple G. Okay, in the telomeres, is T. What just happened? It is T, T, A, G, G, and G. So what I am saying is, see, in the telomeres, in the end regions, the DNA sequence is just this TTA, GGG, TTA, GGG. See, this unit is going to repeat almost 3000 times to 15,000 times. 3000 to 15,000 times the same unit, the same sequence is going to be repeated. So what does I actually mean by here? I mean, see, this DNA sequence, this nucleotide sequence is not actually active. Transcriptionally, it is not active. Okay, so it's just like a simple DNA material which is present in the telomeres, which is not involved in any proteins. It's just like a simple nonsense material present over there. Important point is, with every cell division, do you know what happens? With every cell division, the telomere regions are going to be shortened. For example, if you take this as a normal chromosome, next, do you know what happens? The size of the chromosomes is going to be shortened. The size of the chromosomes is shortened. Exactly, specifically speaking, the telomeres region, some of the telomere region is lost, which means some sequences, okay, for example, 100 sequences, like 50 sequences of this repeats, TTA, GGG repeats are going to be shortened. With every cell division, these units are going to be shortened, 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 shortened. Ultimately, what happens? There will come a time, no longer further shortening of chromosomes is allowed. If a further shortening of chromosomes happens, means the active DNA material will be affected. So what I am saying, see, initially, with every cell division, with every chromosomal division, the telomere size is going to be shrunken down. When the telomere sizes are shrinking down, means this TTA GG repeats are going to be now cutting, 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 cutting. Okay, they are going to be like becoming smaller, smaller, smaller. There will come a time, there will come a time where further shortening of chromosomes, further shortening of telomeres will not occur. Then what happens? Then chromosomes cannot divide. If chromosomes cannot divide, you cannot have cell division to occur. If cells are not dividing, in the place of old cells, new cells are not being replaced. If no new cells are coming, means ultimately you will end up with aging. Okay, that's how we age. So this is how aging will occur. So shortening with every cell division. Okay, let me write it down here. Shortening telomeres, they will shorten or with shortening with every cell division. Okay, but do you think this is good? Okay, we are continuously having cell divisions, right? See, there is also a protective substance which is present in our cells. The protective guy here I am discussing is known as, the enzyme name is telomerase. Now, what exactly is this enzyme telomerase and what it is doing? Telomerase, see, with every cell division, telomere size is getting decreased, right? Now, what this telomerase will do? Telomerase, okay, it will prevent the shortening. The telomerase will prevent shortening. It will prevent the shortening of telomeres. Okay, this is something good or bad? This is absolutely good. Okay, this is absolutely something good, because now, for example, see, now let's take a situation like this. You got exposed to some kind of, exposed to some kind of IR radiation or whatever. You got a mutant. Okay, you got mutations which have occurred in your cells, in all your somatic cells, body cells. Now, instead of having normal amount of telomerase, now you are having super high quantities of telomerase, for example. Now, what will happen? Just think, whenever you having excessive amount of telomerase, do you think you will age? No. See, with every cell division, telomeres are getting coming down, but you are having good amount of telomerase. So, what this telomerase will do? Telomerase will again build the last part. Okay, so you will become immortal. Now no one is going, now you are not going to kill naturally, you are not going to die naturally because you are having good amount of telomerase. Okay, so important points which I want you to know is the two important MCQs are, sir, what kind of enzyme is this telomerase? It is again forming the telomers, right? It is again forming the DNA material. So what kind of enzyme is this telomerase? Okay, see, the answer is, take it down here, it is RNA dependent, not working. Just give me one minute, guys. This pencil is not working. Okay, so this telomerase is RNA dependent DNA polymerase. So the first exam question is this, telomerase. So telomerase, it actually decreases the cellular aging or it increases the cellular aging process? It decreases the cellular aging process. Telomerase is what type of enzyme? It is RNA dependent, DNA polymerase. It forms the DNA, it forms the extra telomers. Okay, it increases the length of the telomers by forming new sequences. It adds more and more TTA, GGG sequences. Okay, now the second question is, so where do you have this maximum quantity of telomerase? In which cells max telomerase is present? The maximum amount of telomerase is present in which type of cells? Now think logically and tell me. So which cells in your body are having maximum capability to divide more number of times? So those cells which are dividing more number of times, we can easily understand, okay, these cells are having more capability to divide, which means continuously the telomeres in the cells are being replenished. That is the reason why these cells are absolutely dividing continuously. Okay, otherwise they will age, they will lose the ability to division, cell division. The maximum amount of telomerase is present in your germ cells. Okay, germ cells. So germ cells are the cells which are present in the gonads, right, in testes and ovaries. Like continuously spermatogenesis is happening 24/7. Okay, now these cells are continuously being divided. The stem cells which are present in the testes, they are continuously being divided, and ultimately they form the stem cells. This process happens for lifetime almost. Okay, now what is happening in the cells? Now in these germ cells, lot of telomerase is present. That telomerase is continuously allowing the cell to divide. Okay, so maximum amount of telomerase is present in the germ cells. Okay, after this, I also want you to know there are certain types of genes called as Sirtuins. Sirtuins. Now, what exactly are the Sirtuins? Now, what exactly are they doing? So, the Sirtuins are a group of genes, okay, which are nothing but the Sirtuins. These Sirtuins are actually the DNA gene. They are histone deacetylator. So, these Sirtuins are histone deacetylators. Now, what is the role, sir? Important point is, see, whenever you activate these Sirtuins, first thing we know, see, to have a good amount of cellular dividing capability, so you need to have good amount of telomerase. Okay, well and good. So that's how you can prevent the aging. That's how you can get the immortality. Okay, anyway, that's not going to be possible. Okay, one way is telomerase. A good quantity of telomerase is something good. Second thing is Sirtuins. Now, what the Sirtuins will do is, the Sirtuins will also prevent aging. Just know this one point. They will also prevent aging. Okay. Now, this was a question which was asked in recent Neet PG exam. See, how to activate the Sirtuins? Once the Sirtuins are activated, for example, if you activate the Sirtuins, now the Sirtuins will prevent the aging. Okay, it will prevent the aging just like telomerase. Now, how to activate the Sirtuins? It's a calorie restriction. calorie restriction. Okay, so if you take less amount of calories, calorie deficit diet. Okay, if you take less amount of calories, that's something really good. For example, we are doing fasting. Whenever you do fasting, that's absolutely good for your health. Forget about the health, actually you can live longer. Why? Because it prevents the cellular aging, it increases the capability of the cellular division. Okay, so two important points. Sirtuins, are they promoting cellular aging, are they preventing the cellular aging? They will prevent the cellular aging. How sirtuins are going to be activated? Sirtuins are going to be activated whenever you take calorie restrictive diet or calorie deficit diet. Now what exactly are these sirtuins? Sirtuins are the histone deacetylators. Okay, histones are the proteins which are present in the DNA. Okay, now by doing the deacetylation of these histones, you can actually prevent the DNA damage and you can further prevent the cellular aging. Okay, now, apart from this, I also want you to know one more point regarding the telomerase. Okay, regarding the telomerase. So, for example, there is this one cell in your body. Okay, there is this one cell in your body, and this cell got really naughty. This cell got really bad. For example, so this cell got crazy because of some DNA mutation. Now this cell, what it is doing is, instead of dividing for every 1 day or 2 day, for example, think this cell should have to divide for every 1 day or 2 days. Now this cell is dividing every hour. Okay, every hour, this cell is now producing its own type of cell. Absolutely dividing, rampage, absolutely dividing. It's a very fast pace. Now, can we call these cells as neoplastic cells? Yes, that's what the property of the neoplastic cells. They will continuously, they are having high mitotic rate. They are going to divide continuously and they will metastasize to the new areas. Now, one important point which I want you to know is, sir, see, cancerous cells, they are absolutely dividing with very fast pace. Now, you can ask me, sir, if you said us, whenever cell, whenever it have undergone certain amount of divisions, automatically the telomere size will decrease. Now, whenever telomere size will decrease, the cell will no longer undergo further division, right? But one important addition to the cancerous cells or the neoplastic cells is, see, neoplastic cells, due to mutations, they will increase the levels of telomerase. Okay, they will increase the levels of telomerase in the cell. Okay, cancerous cells have high levels of telomerase. That's why they are continuously dividing, and they will go to the new areas. Okay, now after this, let me discuss about a few important syndromes which are called as Progeroid syndromes. Okay, you have already watched this one movie, Bollywood movie, which is like, where the guy is undergoing premature aging. Okay, so this one word progeria or progeroid actually means premature mature aging. Now I have already explained to you why we age. The one reason why we age is because the telomeres will shorten in length. Okay, telomeres will go down. But there are certain syndromes because of some gene mutations which we will discuss now. There are a group of syndromes where early aging will occur. Okay, the person is going to age very early. Okay, at 2-3 years he will look like 10 years, 15 years. By 15 years, he will look something like 60 years. Okay, early aging or premature aging. Now, important points which I want you to know is, sir, just give us a few diseases where the patient is going to suffer with premature aging. Okay, now you just think yourself, the one important syndrome which you should never ever forget is Werner syndrome. Werner. Werner. Werner syndrome. Okay, Werner syndrome, not Wermer syndrome. Werner syndrome is absolutely different. This is Werner syndrome. Okay, Werner syndrome. Now, this Werner syndrome is also called as adult progeria. First point is, it's also called as AKA adult progeria. ADULT, adult progeria, which means, see, the patient in his early stages of life. Okay, see, by 10 years, 12 years, like up to his adolescence. Up to his adolescence, the patient is absolutely normal. Okay, but once he get into adolescence, 15 years, 16 years, now the symptoms have started to appear. Now he is looking like a very elderly person. Now he starts to look like a 40-year-old or 50-year-old. Okay, this is adult progeria. Adult progeria is what? It is Werner syndrome. The questions that will come to you repeatedly asked MCQ. One important point is, sir, this adult progeria is due to defective in defect in DNA helicase. Okay, this DNA helicase is an enzyme which helps in DNA replication. Okay, now the defect in this enzyme and the gene related to this enzyme, defect in DNA helicase will lead to progeria. Which type of progeria? Which type of progeroid? Not progeria, progeroid. Which type of progeroid syndrome? That is Werner syndrome, and it have autosomal recessive pattern of inheritance. Okay, it have which pattern of inheritance? Autosomal recessive, also important. Okay, now the second type, which is actually called as progeria. Okay, right now we are discussing all progeroid syndromes, right? The second type is really called as a progeria, also called as very famously known thing. This is Hutchinson-Gilford syndrome. Okay, Hutchinson-Gilford syndrome, which is also called as progeria. Okay, so this is mostly like the scene in that movie, that the Bollywood movie where that Amitabh Bachchan sir is like a very old person. Okay, now what are the important points which you need to know regarding this Hutchinson-Gilford progeria? Two important MCQs here. This is childhood onset progeria. Okay, this is childhood onset, which means the person will start to become old the ages itself. Second thing, what is the defect? Where is the defect present, sir? Defect in, okay, defect in lamin. Okay, defect in lamin. Guys, 1 minute. There is a little technical issue. Let's take a break of 1 minute. Okay, let's take a break of 1 minute. I just want to do something with this pen. It's not writing. Just take a break of 1 minute. We'll be back. Break. Break. Okay, okay, guys, welcome back. Everything got set. Now, what we are discussing is the different types of progeroid syndromes. I have already explained to you progeroid syndrome. Persons are getting aged very early. Okay, now the types of progeroid syndromes which I want you to know is first thing is Werner syndrome. Don't confuse it with Wermer syndrome. Here itself, I just want to know you Werner syndrome. Wermer. Okay, Werner syndrome is a type of multiple endocrine neoplasia type 1. Okay, multiple endocrine neoplasia type 1 is called as Werner syndrome. Okay, multiple endocrine neoplasia where the person is going to suffer with uh, pituitary tumors, parathyroid tumors, and pancreatic tumors. Okay, pituitary, parathyroid, and pancreatic tumors. 3P. Okay, 3P tumors were there. Okay, 3P tumors are seen in Werner syndrome, which is multiple endocrine neoplasia. That's absolutely different. You will study in your endocrine pathology. But here, what I am saying, because of a defect in DNA helicase, because of a defect in a gene called as DNA helicase and enzyme DNA helicase, the patient is going to suffer with early aging, adult onset aging, which is called as a Werner syndrome. The second type is Hutchinson-Gilford syndrome, which is also called as a progeria, the actual real progeria, which is childhood in onset, and defect here is due to lamin gene mutation. Lamin. Okay. Now there is also treatment, which is also important here. The treatment, you can actually treat this condition. The treatment is done with agents called as farnesyl transferase inhibitors. Okay, farnesyl okay, transferase inhibitors. So farnesyl, direct question, farnesyl transferase inhibitors are used in the treatment of progeria. Okay. Now the third type of progeroid syndrome which I want you to know is the Bloom syndrome. Just know this name, Bloom syndrome. BLOOM. Okay. BLOOM. Bloom syndrome. Okay, Bloom syndrome. Now in this Bloom syndrome, what they will ask you is a defect. In Werner syndrome, it is DNA helicase defect. In Hutchinson-Gilford syndrome, it is lamin, not laminin. Laminin is different. This is lamin. Lamin, like is going to be affected. Lamin gene is going to be affected. In in Bloom syndrome, it is a BLM gene. Bloom, BLM. Okay, BL. Just take out the zeros. Okay, zeros. Just think like zero doesn't have any importance. It's a BLM gene. Okay, BLM gene is going to be mutated. Okay, BLM gene mutation will cause Bloom syndrome. And the last syndrome, very, very important, which I want you to know is Rothman-Thompson syndrome. Okay, Rothman-Thompson. Okay, Rothman-Thompson syndrome. So what exactly is this Rothman-Thompson? If you ask me, again, it's also a type of progeroid syndrome. Even in this syndrome, Bloom syndrome, Werner syndrome, in all these syndromes, patients, one thing is clear: all patients will age very early. Apart from that, here in Rothman-Thompson syndrome, the points which I want you to know, for exam purposes, these patients also have certain important features. Okay, apart from early aging, premature aging. Okay, first thing is premature aging, no doubt. Premature aging. Okay, now these patients are going to have the cataract, okay, in their eyes. Okay, in very young age, juvenile cataract. Okay, now these patients are going to have something called as juvenile cataract. Premature aging, juvenile cataract. These patients on their body, they are going to have very sparse hair, sparse hair. Okay, and these patients are also going to suffer with a bone condition called as osteosarcoma. It's a bone cancer. Osteosarcoma. Now in your exam, the question that will come is, in which type of progeroid syndrome the patients are going to have, in which type of progeroid syndrome the patients are going to suffer with osteosarcoma? It is Rothman-Thompson syndrome. In which type of progeroid syndrome the patient is going to have cataract in their eyes, juvenile cataract? Again, Rothman-Thompson syndrome. Apart from this, what else they can ask you in your exam is, sir, in this Rothman-Thompson syndrome, what is the defect? Is it lamin gene defect? Is it DNA helicase gene defect or BLM gene defect? Now here the gene defect which I want you to know is RECQ4. Okay, the defect is REC, okay, Q4. So this is the defect which I want you to know. This is the defect, the gene mutation. So with this, okay, with these four Progeroid syndromes, we have completed the topic of the Progeroid syndromes. Okay, the conditions where the patient is going to suffer with early aging. Now after this, the topic which I want you to know is calcifications. Calcification. See, the patients will also age because of other reasons like free radical damage. In yesterday's class itself, we have discussed free radicals are those substances which are having an unpaired electron in the outer orbits. The free radicals like hydrogen peroxide, hydroxyl ions, superoxide ions. Okay, so superoxide ions, hydrogen peroxide H2O2, and hydroxyl ions. See, all these are free radicals. These free radicals will also damage the cell membrane. They will react with the proteins inside the cell. They will react with the organelles. They will cause a damage to the cell. In that way, they can lead to the aging. And the most common cause of aging is the free radical damage. To prevent the free radical damage, in yesterday's class we have discussed there are vitamins which are acting as antioxidants like vitamin A, vitamin C, vitamin E. What they will do? Vitamin A, C, E will come and destroy the free radicals. Okay, and there are certain important plasma proteins like ceruloplasmin, transferrin. These are the plasma proteins which are acting as antioxidants. Okay, and there are certain important enzymes like glutathione peroxidase, catalase. They will also help in prevention of free radical injury. So you can prevent the free radical injury and you can prevent the aging. Yesterday's class we have discussed vitamins are A, C and E. Plasma proteins are transferrin and ceruloplasmin. Enzymes, the enzymes which are helping, okay, the enzymes which are helping in prevention of the free radical injury is catalase, glutathione peroxidase. Okay, so apart from that, okay, the topic is completed. Apart from that, the next topic which I want you to know is the calcification. Calcification means deposition of calcium in different tissues leading to ossification. Okay, more kind of ossification. So calcification is of how many types? There are two types of calcification. Okay, lots of times questions have been asked from this area. Okay, calcification is of how many types? Two types. Now, what are these? The first type is called as dystrophic calcification. Dystrophic calcification. Dystrophic calcification. And second type is metastatic. Okay, calcification. Okay, so dystrophic calcification, metastatic calcification, what are the differences? Now first let's see what exactly is dystrophic calcification. See, this dystrophic calcification is nothing but, see, dystrophy, something like destruction, destroyed or dead. So in those dead tissues, calcium will go and precipitate there and forms calcium depositions. Calcification is happening in the dead tissues. So that type of calcification is called as a dystrophic calcification. But if you look at the plasma levels of calcium, the plasma levels of calcium is absolutely normal. Now direct question is, dystrophic calcification, is it happening in hypercalcemic states? No, it's happening in dead areas, in dead tissues, necrotic tissues. But if you look at the blood calcium levels or the plasma calcium levels, they are absolutely normal, no rise in calcium levels. Okay, now on the other hand, what exactly is metastatic calcification? Metastatic calcification means if pathologically, okay, pathological increase in plasma calcium levels because of some reason, okay, we'll discuss, because of some reason, man, if calcium levels are elevated in the blood, so what all this extra calcium will do? All this extra calcium will allow to precipitate in different tissues which are absolutely healthy. For example, they will go and deposit in kidneys, form stones. So this is an example of metastatic calcification. So the main important difference between dystrophic calcification and metastatic calcification is such the plasma levels of calcium. In dystrophic calcification, plasma levels is normal. In metastatic calcification, the plasma levels is pathologically elevated or highly increased. Okay. Now, first let's talk about the examples, okay, of dystrophic calcification. Now, can you give us, please, can you give us some examples of the dystrophic calcification? Okay. So, if you know some examples of dystrophic calcification, you can all the time put it in the chat box. Okay. Come on, guys. Dystrophic calcification. Can you tell me? One very important example is there, and that will be coming repeatedly in the exam. Dystrophic calcification. At least I want to listen that one thing from you. Come on, guys. We start with the letter P. Come on. Is Samoma bodies. PSA Samoma bodies. Okay, I want you to know this one thing. Sir, Samoma bodies are example of dystrophic calcification. If you ask me Samoma bodies, what exactly are they? In a very simple way. For example, this is a tumor cell. Okay, this is a tumor cell. Okay, now these tumor cells are surrounded by, okay, this is something pathology, right? Okay, tumor cells, especially the dead tumor cells, now they are surrounded by walls of calcium. Calcium is now coming and depositing. Calcium is now coming and depositing in the form of layers, just like an onion skin. So the tumor cells surrounding with the calcium is called as a Samoma bodies. Okay, and these Samoma bodies, repeatedly asked MCQ, are seen in which conditions? Samoma bodies are seen in which cancerous cells will love to have this type of calcification? So, seen in the mnemonic which I want you to know is most PG. The most PG is an example of dystrophic calcification, as well as the most PG is this is a mnemonic. Okay, I'm not, I haven't yet told you what exactly is this most PG. Most PG are the conditions where you will see Samoma bodies. Now let's see what exactly is this most PG. M stands for meningioma. Okay. O for papillary carcinoma of papillary carcinomas. Okay. Every time listen, whenever you hear about the word papillary carcinoma, think about the Samoma bodies. Papillary carcinoma of ovary, and S for papillary carcinoma of salivary gland, and T for papillary carcinoma of thyroid. Papillary carcinoma, CA for carcinoma means cancer. Papillary carcinoma of thyroid. Now, whenever you suffer with, see, there are different types of thyroid cancers, papillary cancers, okay, follicular cancer, papillary cancer, medullary cancer, different types of thyroid cancers are there. But all the types of thyroid cancers, will they show the Samoma bodies? No, especially the papillary cancers of ovaries, papillary cancers of salivary gland, papillary cancers of thyroid, they will show this Samoma bodies. And P stands for prolactinoma, prolactinomas, okay, tumor to the lactotropes, and G for glucagonoma. Okay, glucagonoma. So, what I am saying is, first thing, Samoma bodies are example of direct question. Samoma bodies are the example of dystrophic calcification, are the example of metastatic calcification. Simple, they are example of dystrophic calcification. What exactly are Samoma bodies? Tumor cells surrounded with walls of calcium is called as Samoma bodies. In which conditions you will see Samoma bodies? I have given you the mnemonic meningioma, most PG. Okay, meningioma, papillary carcinoma of ovary, thyroid, as well as salivary gland, and prolactinomas and glucagonomas also you will see such kind of Samoma bodies. And other places where you can see such type of dystrophic calcification is tuberculosis. Okay, whenever you have that infectious foci, okay, infectious foci, which is called as a Gons focus. Okay, I hope you already know this. Whenever you have that infectious foci is going to be calcified, which is called as the Ranke's complex. Okay, so in tuberculosis you will see dystrophic calcification, and in the blood vessels, whenever you have atherosclerotic plaques, okay, atherosclerotic plaques where with the duration, with the time, that atheromas will also calcify. Okay, atheromas will love to calcify. Calcification will occur. That's also example of dystrophic calcification. Okay. Now, on the other hand, now let's talk about the metastatic calcification. So, in which conditions metastatic calcification occurs? Now, what is the important point which I have already asked you to remember? In metastatic calcification, what is the blood levels of calcium? Pathologically elevated. The blood levels of calcium are increased so much. Now, let's see one by one what are the conditions where the blood calcium levels are elevated and that is leading to further calcification, which is a metastatic calcification. Now, let's write one by one. Hyper, para, thyroidism. Now, we all know parathyroid hormone, PTH. It's coming from where? Parathyroid hormone is coming from the parathyroid glands. Now, the chief cells of parathyroid gland produces the parathyroid hormone, and parathyroid hormone normally regulate the blood calcium levels. It increases the blood calcium levels in physiological limits. But for example, if you have a condition called as parathyroid adenoma, where the person is producing excessive amount of parathyroid hormone, the patient is going to suffer with hyperparathyroidism. In that conditions, what happens? If you check the blood levels of calcium, the blood levels of calcium are pathologically elevated. Now, this calcium will love to deposit in different tissues that will lead to metastatic calcification. And the other examples are renal cell carcinoma. I'm not going in detail why the calcium levels are exactly elevated. Just here, at this point, at this level, at the basic level, what I want you to know is, so these are the conditions where the blood levels of calcium are elevated in renal cell carcinoma and especially in sarcoidosis. Okay, sarcoidosis, two important points I want you to know is blood calcium levels are elevated as well as the angiotensin converting enzyme ACE, angiotensin converting enzyme levels are also elevated. Okay, this is just a medicine point, but here what I want you to know is there is a condition called as sarcoidosis where the calcium levels are elevated, and the fourth condition is multiple myeloma. Okay, multiple myeloma is a bone condition where the lytic lesions are going to be seen in the bone. Bones are going to be destroyed. Okay, bones are pathologically destroyed. When the bones are being pathologically resorbed, all the calcium from the bone, it's coming where? All the calcium from the bone is coming into the blood, and blood levels of calcium is elevated, and that calcium is going to get deposited in the tissues, causing metastatic calcification. So these are the examples which I want you to know regarding metastatic calcification. Next, what I want you to know from this topic is that 2 points. Okay, two important points. What are they? So, okay, in metastatic calcification, calcium is coming and getting deposited, right? What is the first place of calcium deposition? What is the first site where this calcium will come and deposit? It's the mitochondria. Even in cellular injury also we have discussed large flocculent amorphous densities are characteristic for irreversible cell injury. So all the time remember calcium loves to go to mitochondria. This calcium will go and precipitate in the mitochondria in the cell. What is the first place it will go and deposit? The mitochondria. The second, the one exception is exception in the kidneys. In which organ calcium is not binding to the mitochondria mainly is a kidney, sir. In kidneys calcium will go and deposit in the basement membrane. Okay, it now getting a deposit in the basement membrane. So these are the exception. Calcium will go and bind with which organelle? First it is mitochondria. Exception is kidneys. In the kidneys, calcium will go and precipitate in the basement membrane. So these are the two types of calcification. These are the miscellaneous topics which I want you to know. Now after this, I want to just have a rapid review kind of thing. Okay. Now we'll be discussing in a question format. Okay, let's see how good you are. Guys, from now just try to answer. From now, the topic is completed. The topic of cell injury is completed. Just try to check yourself how good you are. Now, what is the most common cause of cell injury? The most common cause of cell injury is ischemia, right? No, it is hypoxia, sir. Hypoxia. Okay. Now, what is the most common cause of hypoxia? The most common cause of hypoxia is ischemia. Already we have discussed this. Ischemia means decrease blood flow. Hypoxia means decrease oxygen supply. Now, the type of hypoxia seen due to cyanide poisoning, the question which was asked in the recent exams. Now, whenever you have cyanide toxicity, because of some reason you took the cyanide, now immediately you are going to die, definitely. Why? What exactly happens? I have already explained to you in the topic of types of hypoxia. See, whenever you take cyanide, what will happen? It will cause histotoxic hypoxia. If it causes histotoxic hypoxia, the cyanide is going to enter into the complex 4 of electron transport chain, so that you cannot able to use, your tissues cannot able to use the oxygen. So the problem lies at the level of tissue. So this is an example of histotoxic hypoxia. Okay, so type of hypoxia seen in cyanide poisoning is histotoxic hypoxia, sir. Histotoxic. Now, cell most sensitive to hypoxia. Which cells in your body are most sensitive to hypoxia? Brain. Okay, brain, especially neurons. Okay, in the brain, yeah, the cells, the structural units. Okay, the units are the neurons. But here I want you to know a bit more detail. See, it's the pyramidal cells of hippocampus. Okay, which cells are most sensitive? Brain is most sensitive to hypoxia. Neurons are most sensitive to hypoxia. Even in neurons, which neurons? It's the pyramidal cells of hippocampus are more sensitive. Okay, main, at least know this one thing. Okay, even in cerebellum, there are cells called as the Purkinje cells. They are also most sensitive. Okay, so pyramidal cells of hippocampus are most sensitive, and the cells more resistant to hypoxia are what? Fibroblast. We have already discussed this, and our chapter name cellular injury. The term cellular pathology, okay, or cellular injury, pathology or injury, it's one and the same. The term exactly we should use cellular pathology. The term cellular pathology was given by a scientist called as Rudolf Virchow. Why I am saying this is long back, very long back, this question has been asked. Okay, Rudolf Virchow is the scientist who gave the term cellular pathology. Okay, now after this, let's let's discuss about the cellular adaptations. Now, what are the cellular adaptations which we have discussed so far? Cellular adaptations are, sir, like hypertrophy, hyperplasia, metaplasia, okay, atrophy. These cellular adaptations, are they reversible or irreversible? See, whenever you put stress on a cell, whenever you are putting stress on a cell, it will first try to adapt. Whenever you take the stressor out, whenever you take that stressing agent out, automatically cell will become normal. Cell will be happy. Okay, no stress. I will come back to normal. Like, normal shape, normal size, to normal type. So usually all the cellular adaptations are reversible. No doubt they are reversible. They are not irreversible. Okay. Now see, all of the following are examples of cellular adaptations except, now see here guys, hypertrophy, is it an example of cellular adaptation? Absolutely. Hypertrophy is increase in the cell size. Hyperplasia, increase in the cell number. Atrophy, whenever you don't use a tissue, it will undergo atrophy, decrease in the number of cells as well as decrease in the size of cell. Atrophy. Atrophy is also a type of cellular adaptation. But see here, metaplasia, the examples I have given you, change in one type of cell to other type. Metaplasia is also an example of cellular adaptation. Everything is good so far. But the dysplasia, sir, dysplasia, what exactly is dysplasia? Cell have gone totally crazy. Now it is no longer able to take the stress. Now you can't even identify what type of cell this is. Loss of cellular differentiation. You cannot identify whether it's a epithelial cell, whether it's a neuron. Absolutely loss of differentiation. So dysplasia or dysplasia is an example of cellular adaptation. The cell is adapting or cell is going absolutely crazy. This dysplasia is not a cellular adaptation, not cellular adaptation. Okay. Now myositis ossificans. Now what exactly is myositis ossificans? We have discussed. Just 1 minute, guys. My phone got like, yeah. Okay. Now see, myositis ossificans. What exactly is this myositis ossificans? The name itself is there. Myositis, inflammation in the muscle, trauma to the muscle, leading to calcium deposition in the muscle. Of course, this is an example of dystrophic calcification, no doubt. But myositis ossificans, here the muscle cells are now changing some sort into a bone-like. So one type of cell is now changing into other type. So myositis ossificans is an example of. It is an example of metaplasia. Okay, it's an example of metaplasia. Okay, now my question, first microscopic change or morphological change? The first microscopic change in reversible cell injury. In reversible cell injury, what is the first microscopic change? What can you actually appreciate? Okay, oh my god, the cell is now bulging. That's the hydropic change or cellular swelling. So the first microscopic change what you can see is cellular swelling. Okay, cellular swelling. Now what is the nuclear change? I'm not asking about just a cellular change. Specifically inside a nucleus, what kind of changes will be seen in reversible cell injury? With the reversible cell injury, what is the change? Sir, I have already explained to you. Now sir, in reversible cell injury there is no ATP production. Whenever there is no ATP production, cell wants to get the energy by somehow. So what happens? Aerobic respiration was shifted into anaerobic respiration. Whenever there is anaerobic respiration, lactic acids will be produced. Lactic acid means acidic pH. That acidic pH will cause clumping of chromatin. Inside the nucleus there is something called as a chromatin. That chromatin will now starts to clump. Not pycnosis, karyorrhexis or karyolysis. Pycnosis, karyorrhexis, karyolysis are something seen with the irreversible cell injury. Now here, now what we can see is the with reversible cell injury, the nuclear changes which are visible are clumping of chromatin. Okay, important word, clumping of chromatin. Clumping of chromatin. Okay, now post cell death, inflammation is seen in. Now my question for you guys, cell is dead. How many types of cell can die? The major two types are apoptosis and necrosis. The major two types of apoptosis and necrosis. Now in these two, apoptosis is programmed cell death. Cell have to die. Cell is deciding itself, I have to die. Now, in apoptosis, will there be any inflammation? No, there is no inflammation in the tissue. Tissue have to die, or that particular cell have to die, so it is dead. So there is no surrounding inflammation. But necrosis is like a murder. There will be a lot of havoc. When in a place of murder, there will be a lot of disturbance, right? Police will be coming, like too many relatives will be coming. So much nonsense will be happening there. So it's some kind of a inflammation. So post cell death, inflammation is seen in necrosis. Which type of cell death? Necrosis, not the apoptosis. Okay, done sir. Gel electrophoresis pattern of apoptosis and necrosis. I hope you guys are excellent here, excellent by this time now. Just tell me, you can actually identify, okay, cell is dead. You can actually identify, okay, this cell have undergone apoptosis and necrosis by a study called as gel electrophoresis. Now, in apoptosis, the DNA, okay, is going to arrange in which form? It is step ladder pattern. Step ladder pattern. Step ladder pattern. In necrosis, it will arrange in the form of smear pattern. Smear pattern. Okay, step ladder pattern or smear pattern. Okay, all the answers were also given here and the PPT will be shared in the group. I don't think yesterday's PPT was shared, but yesterday's PPT and today's PPT combinedly will be shared in the group with questions and answers as well. Now, what is the most common type of metaplasia? The most common type of metaplasia is squamous metaplasia. Squamous type of metaplasia. Okay, there are different types of metaplasia. The squamous metaplasia is most common. And I have also given you the types of examples for the squamous metaplasia. One is the Barrett's esophagus, where the squamous epithelium is now being changed into the squamous epithelium is now changing into intestinal type of columnar epithelium with the goblet cells. The example is Barrett's esophagus. Because of the acid reflux, because of the gastrointestinal reflux disease, acid is being refluxed back from the stomach into the esophagus, leading to metaplastic change in the lower one third of the esophagus. I have already explained this to you. Now, which vitamin deficiency? Okay, now I also explained which vitamin deficiency lead to metaplastic transformation. Okay, especially this happens in the cornea. Whenever you are deficient of vitamin A, important MCQ, vitamin A deficiency will cause metaplastic change. Okay, your cornea will become more cloudy. Okay, now anaplasia is defined as, see, anaplasia anaplasia is more like dysplasia. You can use the terms like as like one another. Anaplasia is loss of differentiation. It's a hallmark of cancer. Okay, it's a hallmark of cancer. Anaplasia, dysplasia, they are almost one and the same. Now, question is the hallmark. Okay, the hallmark of malignant transformation is nothing but this anaplasia only. Okay, the hallmark of malignant transformation is anaplasia, or you can also use dysplasia. Okay, so loss of differentiation. You cannot identify what the type of cell is. It's not a cellular adaptation. Okay. Now, what is the, yes, let's come back. What is the earliest organelle involved in cell injury? In cell injury, the earliest organelle all the time, for everything, the answer is mitochondria. What is you are going to see in the mitochondria? In the mitochondria, calcium is now going to come and accumulate. Calcium will now come and accumulate in the form of large amorphous flocculent densities. Once you see this, it is irreversible cell injury. But initially speaking, what happens? So whenever there is hypoxia, see, this is very important. Whenever there is ischemia, that will cause to hypoxia. Whenever there is no oxygen, cell cannot produce ATP. Where ATP is getting produced? Inside the mitochondria. So first cell organelle that is affected is mitochondria. Okay, in reversible cell injury also, the first cell organelle is affected is mitochondria. No ATP production. That is in reversible cell injury. What happens in irreversible cell injury is that inside the mitochondria, all the calcium will now come and get deposited. That is called as a large flocculent mitochondrial densities. Now, myelin figures, my question to you. Myelin figures are seen in reversible cell injury or irreversible cell injury? I have explained to you. When when the cell is swelling, okay, the cell is now swelling. Now some amount of the phospholipids in the cell membrane, they will be teared away, they will be detached from there, and even your cell organelles like endoplasmic reticulum, Golgi complex, they are also surrounded by the membrane, right? They are also having their own membrane. That these organelles will also swell up so that the membrane is damaged, and these membrane particles, they will curl up. Why? Because they are hydrophobic in nature. This cell membrane, these particles, these phospholipids are hydrophobic in nature, so they will curl up in the form of these whorls. Okay, they are now curling up. So these are nothing but the myelin figures which are seen in reversible cell injury, but also seen in irreversible cell injury. But if they directly ask you the question, they are seen in reversible cell injury or irreversible cell injury. So with reversible cell injury usually generally. But if the option is there both, it's seen in both reversible as well as irreversible cell injury. But my question here is, myelin figures are made up of, they are made up of phospholipids. Phospholipids. And nothing but a cell membrane. Cell membrane damaged and now it is curling up. Okay. Now, what is the pathognomic feature of irreversible cell injury? It is excessive cell membrane damage. If once the cell membrane is damaged beyond repair, too much damage to the cell membrane, irreversible cell injury. Hallmark, here they are specifically asking pathognomic feature. I have explained to you, it is large flocculent mitochondrial densities. Nothing but the calcium aggregation inside the mitochondria is a hallmark feature or characteristic feature. Now, what is the most common type of necrosis? From here, you can just go on very fastly. What is the most common type of necrosis, guys? The most common type of necrosis is fibrinoid necrosis, fat necrosis, liquefactive necrosis. No, it is coagulative necrosis. Coagulative necrosis, sir. See, only those students who have attended the previous classes, they can only understand. Okay, only they can understand. Okay, so most common type of necrosis is coagulative necrosis, no doubt. Now, what is the microscopic appearance in the coagulative necrosis? Okay, most of our body tissues except brain and pancreas, most of our body tissues, the solid organs are undergoing coagulative necrosis, no doubt. Now, if you put it under the microscope, if you see the structure of the cells is preserved, the structure of the tissue is preserved. So it looks like what? Come on, guys. Okay, let me check the comment section. Come on. See, only those students, again I am repeating, only those students who have attended the previous classes. Okay, the previous classes. This is what I am exactly doing is I am taking up all the questions which has came in the previous exams. Like I am just only discussing them. Okay, so please try to watch the previous videos. Okay, we have already had 2 classes on the cellular injury. Please watch them and just try to come and try to solve these questions. Okay, now what is the microscopic appearance in the coagulative necrosis? It is a tombstone appearance. Tombstone appearance. Tombstone appearance is seen in coagulative necrosis, and the important point is in coagulative necrosis, what is happening? Denaturation of proteins. Proteins are going to be denatured. Tissue architecture is preserved. Tombstone appearance is seen, and the dead cells are called as ghost cells. All points discussed. Okay, all points we have discussed. Now, pancreatic parenchyma if it undergoes necrosis because of acute pancreatitis or whatever the reason, if pancreatic parenchyma is undergoing necrosis, it undergoes which type of necrosis? Parenchyma, the actual pancreas. Pancreas will undergo liquefactive necrosis. Liquefactive necrosis. Pancreas and brain. The three important examples of liquefactive necrosis is abscess. Abscess anywhere in your body. Abscess is an example of liquefactive necrosis. In brain, in central nervous system, because of the high enzymatic content in the brain and spinal cord, as well as in your pancreas, because of the high amount of enzyme activity, it will undergo liquefactive necrosis. The tissue architecture is not preserved. Okay, peripancreatic fat. The fat around the pancreas will undergo fat necrosis. Fat necrosis. Okay, well and good. Now in fat necrosis, I have explained to you. In fat necrosis, all the fatty acids are coming, right? The adipose tissue is now dying. Adipose tissue is dead. From the adipose tissue, he is coming out. Fatty acids are now being released. I have explained to you. Fatty acids love to bind with calcium. This process is called as binding of fatty acids with calcium is something called as saponification. Because of saponification process, wherever there is fat necrosis, their calcium is going to appear in the form of chalky white appearance. There will be calcium and it appears in the form of chalky white. So chalky white appearance is also seen in fat necrosis. Okay, so chalky white appearance is in which type of necrosis? Fat necrosis. Now cottage cheese like. Okay, cottage cheese like. So necrosis has happened, but because of the presence of high lipid content. See, for example, to my lungs there is an infection called as a TB. TB is because of Mycobacterium tuberculosis. Okay, the organism causing it is Mycobacterium tuberculosis. These are the rod-shaped bacilli which have high lipid content in their cell wall. What is that lipid content? Mycolic acid. Now this organism is dividing, attacking the cells, causing destruction of the cells, leading to necrosis. Now if you look at my lung, there the necrosis will look like cottage cheese. It will look like a cheese, like a paneer. So cottage cheese like appearance is seen in which type of necrosis? Caseous necrosis. Caseous necrosis. Okay. Now ash of bodies. Now my question to you guys, ash of bodies are seen in which condition? Guys, if you can able to remember, just tell me, ash of bodies are seen in which condition, guys? Ash of nodules, ash of bodies, they are pathognomic, especially in your second, if you are especially who have studied the pathology, just tell me. Ash of nodules or ash of bodies, Anitschkoff cells, ash of bodies, McCallum plaque, all these are seen in a disease called as rheumatic heart fever. Okay, in rheumatic heart fever, ash of bodies are seen. These ash of bodies are nothing but an example of fibrinoid necrosis. Fibrinoid necrosis. Okay. See, ash of bodies are example of fibrinoid necrosis. Here I have also given you the other examples. Fibrinoid necrosis is also seen in whenever you are having any damage to your blood vessels, inflammation of the blood vessels, there is a vasculitis, malignant hypertension. All these are example of in malignant hypertension, the vessels will be damaged and that damage is nothing but the fibrinoid necrosis. Okay. Now, physiological apoptosis is seen in physiologically. Okay, certain cells in your body should die. Certain cells in your body should die physiologically. What are the examples? For example, I have explained to you during embryogenesis. Okay, in between fingers, whatever the cells were there, in between the fingers, these cells need to be apoptosed. These cells need to be killed. Not killed actually, they have to die. Okay, they have to commit suicide. So these cells are dead so that we are having proper digits. So during embryogenesis, apoptosis will happen. Also self-reactive T lymphocytes or B lymphocytes, self-reactive lymphocytes need to be eliminated. We don't want those cells. So those cells which are self-reactive, they will automatically undergo apoptosis. The two physiological examples of apoptosis are during embryogenesis, the webbed cells between the fingers undergoes apoptosis, and elimination of self-reactive lymphocytes is also an example of physiological apoptosis. And also remember, apoptosis, is it physiological or pathological? Apoptosis is all the time necrosis is all the time pathological, but apoptosis is both physiological as well as pathological. Okay. Now also remember this point, define atrophy. Atrophy, most of the students will think atrophy is decrease in the size of an organ. Why a tissue size is getting decreased? Okay, The size of the tissue is getting now smaller and smaller. Example is involution of thymus. Involution of thymus. The thymus which is present in our mediastinum, thymus with age, it is going to involute. Atrophy is happening. Now this atrophy is due to decrease in number of cells as well as decrease in the size of the cells. Both decrease in size as well as decrease in number. And involution of thymus is also an example of physiological apoptosis. Okay, also remember that. Very important. So here we have discussed about the physiological apoptosis. Done. Now example of pathological apoptosis is councilment bodies. Councilment bodies are pathological example of apoptosis. Now if you ask me explain, see, now there is, for example, if you got infection with the hepatitis C virus, okay, now you got infection. Now whenever you got infection to your liver, now I have already explained to you, this is the hepatocyte, liver cell. Now virus have came into the cell. Now this viral infected cell, viral infected hepatocyte, it knows, oh my god, something bad guy is there inside me. If this hepatocyte is still living, if it is living, further viral replication will happen and virus is going to replicate and it's going to, at one point it is going to burst the hepatocyte and more viral cells are, more viruses are going to, more virions are going to come out and will attack the surrounding hepatocytes. Now what will happen? Now what this viral infected hepatocyte will do? Now it will, by itself, it will commit suicide. So this is something absolutely pathological. This is not good. This is pathological, but it is programming its death. It is programming its death. So this is pathological example of apoptosis. So the dying hepatocytes are called as the councilment bodies. In which condition you will see these councilment bodies? Mainly these are seen in viral hepatitis as well as yellow fever. In viral hepatitis as well as yellow fever, you will see councilment bodies. No one is going to ask you yellow fever, but at least remember, councilment bodies are dying hepatocytes, apoptosing hepatocytes in viral hepatitis. Okay, now this one is not needed for you. This is not needed. At least I want you to know this thing. Physiological hyperplasia. At the same time, both hyperplasia and hypertrophy is happening in which organ? Both at the same time. So it is uterus during pregnancy. So during pregnancy, both hypertrophy will happen as well as hyperplasia will happen. But who is more? Hypertrophy is more than hyperplasia. Okay, hypertrophy is more predominant. In uterus during pregnancy, both hypertrophy and hyperplasia will happen. At the same time, in breast also. See, breast during puberty. In breast during puberty, both hyperplasia and hypertrophy both will happen, but hyperplasia is more than hypertrophy. Okay, two important points which I want you to know. So at the end, if you want to know one single point before going to the exam, it's both hypertrophy and hyperplasia happens in uterus as well as breast. That's it. Okay, if they specifically ask you in a lactating breast, okay, not during pregnancy, after pregnancy, now she is lactating. Now what happens? It's a hypertrophy. Now we all know a lactating female is going to have a bigger breast, right? Okay, she's going to have a bigger breast. This bigger size in breast is because of hypertrophy or hyperplasia. It's mainly because of the hypertrophy. Okay, not mainly, we should say it's because of hypertrophy. That's it. Okay. Now, what is the most important? If they ask you a question like this with 4 answers, most important light microscopic feature of irreversible cell injury. If it is an irreversible cell injury, what can we actually see? Okay, it is irreversible. Okay, light microscopic feature of irreversible cell injury. Guys, I want you to answer this. If you are really good, okay, if you think that you are really good, just try to answer it. Option number A, B, C, D. What is the most important light microscopic feature of irreversible cell injury? Come on guys, option A, B, C or D. Amorphous densities inside the mitochondria. Is it a feature of irreversible cell injury? Cell membrane blebs or loss of microvilli, ribosomal detachment from endoplasmic reticulum, or option number D, nuclear changes like pycnosis, karyorrhexis or karyolysis. Now, what is your option? Option A, B, C or D? Come on. See, someone is answering ribosomal detachment from endoplasmic reticulum. See, during reversible cell injury, what have I explained to you? The cell is going to swell in size, more water is coming, cell organelles will also swell in size. I have explained to you, for example, if you are a male, when you are becoming more and more fluffy, when you are becoming more and more obese, what will your girlfriend will do? She will simply leave you. Okay, you are not looking good. She will simply leave you. That the same example I have given you on that day also. During reversible cell injury, more water will come into the cell. Cell is undergoing hydropic change. Okay, cell is undergoing hydropic change. So that even cell organelles will swell. So endoplasmic reticulum, the ribosomes which are attached to endoplasmic reticulum, they will move away. That is seen in reversible cell injury. Okay, and Roy and most of the students are answering A. This is where most of the students will go wrong. See, most of the students will think, sir, amorphous, large flocculent densities in the mitochondria. Yes, absolutely, they are a feature of irreversible cell injury. No doubt, they are a feature of irreversible cell injury. But are you able to see these densities under light microscopy is the question. You cannot see this, okay, you cannot see them in light microscopy. You can only see them in electron microscopy. You can appreciate these large flocculent densities in electron microscopy. So here this is a tricky question. The answer here is the nuclear changes, pycnosis, karyorrhexis and karyolysis. Now yes, pycnosis, karyorrhexis and karyolysis are a feature of irreversible cell injury. Okay, which can be appreciated in the light microscopy also. Okay, I hope it's clear for you. What is the sequence of nuclear changes in necrosis? The sequence of nuclear changes in necrosis is cell death, right? The sequence is pycnosis, karyorrhexis and karyolysis. Okay, I want you to know this. The cytoplasmic changes is not that important. If you want to know, nucleus is undergoing death, pycnosis, karyorrhexis, karyolysis. Now, if you see the nucleus, there will be a lot of vacuolization that will occur, that will look like a moth-eaten appearance of cytoplasm. Okay, moth-eaten appearance of the cytoplasm is seen in, again, cell death. It's a cytoplasmic change. Nuclear change is pycnosis, karyorrhexis, karyolysis. Moth-eaten appearance of the cytoplasm is seen again in necrosis, cell death. Okay. Now, apoptotic bodies, explain to you. Okay, apoptotic bodies. This is not a question. It's a direct answer. Apoptotic bodies means after pycnosis, karyorrhexis, karyolysis, now cell is now dying. Now cell is now pinched off into small particles. The entire cell is now broken down into small particles. Now you need to clear these small particles away. That's a phagocytosis. That's a total different story. Now my point is, after the cell death, small bodies, apoptotic bodies, what exactly are they? They are nothing but cytoplasm organelles with the nuclear fragments. Okay, a big cell was now chopped off into small particles. With cytoplasm is there, cell membrane is there, nuclear fragments are there. So these small particles are called as apoptotic bodies. The question asked is, apoptotic bodies are made up of, yes, cytoplasm, small still organelles are there, and nuclear fragments. Now what I have explained to you, when a cell is undergoing apoptosis, what will happen? Now the dying cell, it will express, now this dying cell, now to outside it will express what? To outside it will express something called as phosphatidylserine. Now this phosphatidylserine is going to be identified by the macrophages. Now macrophage will coming, now it's coming. Now it's seeing, okay, cell fragment, okay, apoptotic body is seen with expression of phosphatidylserine. Now macrophage, what it will do? It will go and engulf and will simply clear out the apoptotic bodies. So the phospholipid which is helping in phagocytosis. What is that phospholipid? Phosphatidylserine. It's a phospholipid. It's a component of cell membrane which is all the time expressed towards the cytoplasm, but in apoptotic cells it is expressed outside. Okay. Now, guys, what is the cluster designation marker of death receptor? Now I have explained to you, this is a cell which is undergoing apoptosis. Okay, which type of apoptosis? Extrinsic pathway. Okay, extrinsic pathway means on the surface of cell there is a receptor, sir, which is called as a death receptor. Death receptor. Now, whenever you come and stimulate this death receptor, okay, the death receptor is also called as FAS. Okay, FAS or death receptor, which is also called as CD95. CD95 is the death receptor. When you stimulate this death receptor, the extrinsic pathway of apoptosis is going to be activated. Extrinsic pathway is activated. Okay, so the cluster designation receptor is CD95, extrinsic pathway of apoptosis. Okay, sir. Now, this P53 is absolutely different thing. In the topic of inflammation also we'll study about this P53. This P53 is present on chromosome number 17. Just if you want to know, P53 is a very guardian angel. P53 is a guardian angel of the cell. It will prevent the how to say? It will prevent the cell death. It will prevent the cancers. P53. Now P53 is located on chromosome number 17. It's a guardian angel of the cell, policeman of the cell. It will prevent the cancers. But anyway, this topic is not needed for us right now. Now, initiator caspases we have discussed in the topic of apoptosis. Sir, in the topic of apoptosis, there are these important enzymes called as caspases, cysteine aspartases. Cysteine aspartases. They will this caspases like executionary caspases, initiator caspases. They will activate proteases, endonucleases. At the end of the day, cell death will happen. Right now, let's come back. Let's see how many types of caspases are there in apoptosis. There are two groups of caspases. First caspases are initiator caspases, sir. Initiator caspases, and also caspases called as sir executionary caspases. This one, executionary caspases. Executionary caspase is the final fellow. Final fellow. Initiator caspases will activate executionary caspases. Executionary caspases activate proteases, endonucleases, so that cell death will occur. Direct question is, who is the executionary caspase? E. We will write E something like this, right? E. Just flip the E like this. So if you flip the E, it will become letter 3, the number 3, number 3. So executionary caspase, one single answer is 3. Executionary caspase is 3. Now, if I am talking about initiator caspases, the initiator caspases are different. Different in intrinsic pathway of apoptosis. See, there is intrinsic pathway, extrinsic pathway. In intrinsic pathway, initiator caspase is different. It is 9. It's 9. In extrinsic pathway, it is mainly 8. 9 and 8 are initiator caspases. 3 is the executionary caspase. Okay. Also explain to you caspases, what they will do. Caspases are enzymes, sir. I have explained to you. Cysteine aspartases. Wherever there is an aspartate residue, there it will go and cleave. Okay. So caspases, what they will do? Caspases cleaves the proteins at which residues? At aspartate residues. Okay. Regarding P53, we will discuss about this later. Okay. Also, in the previous class, I have explained to you what are the stress sensors inside a cell. The stress sensors are BAD, BIM, NOXA, PUMA, BID. All these are the stress sensors. Also explained to you in the topic of apoptosis. There are certain anti-apoptotic genes. Anti-apoptotic genes means the genes which doesn't allow the cell to undergo apoptosis. They are good. They are not letting the cell to die. Okay, all the time they are preventing cell death, preventing apoptosis. What are they? Main fellow is BCL2. Okay, it is BCL2. Okay, BCL2, BCL1, MCL, BCLXL. Okay, all these BCL1, BCL2, MCL, BCLXL. All these are the anti-apoptotic genes. Anti-apoptotic genes. Okay, so at least try to remember these things. And last slide, which I want you to know, is what is the dye used for diagnosis of apoptosis? If you want to know the cells which are undergoing apoptosis, the dye which is used is annexin 5. Annexin 5 is the dye used for apoptosis. Okay. Now, caspase independent cell death is known as, see, it is a cell death. First of all, it's a cell death. How many types of cell death is there? Necrosis, apoptosis. Apart from this classical two, there is something called as necroptosis, pyroptosis. Now, what exactly is this necroptosis? A combination of necrosis as well as apoptosis. Now, in necroptosis, caspases are not involved. Caspase independent cell death. No caspases are involved. I have explained to you the pathway also. That human necrosis factor receptor, all the pathway I have explained. So caspase independent cell death is called as necroptosis. Okay, necroptosis. Here it's a necroptosis. Okay. Now pro-inflammatory programmed cell death. Again, it's a programmed cell death. It's a program, which means definitely like apoptosis. Like there is a program is there. But in apoptosis, do you expect inflammation? Do you expect inflammation in apoptosis? So in necrosis, inflammation will be there. Post necrosis, there will be inflammation. In apoptosis, there is no inflammation. But here the question say pro-inflammatory means inflammation is there and it's a programmed cell death. What is this? Pro-inflammatory programmed cell death is pyroptosis. Okay, so pro-inflammatory cell death is pyroptosis. Okay, pyroptosis, where the patient is going to especially produce interleukin 1 that will cause fever. Pyroptosis means fever. The patient is, after the cell death, the patient is going to have fever. Okay, now sir, the pigment which is synthesized from tyrosinase. I have already explained to you in the cellular accumulations pigment part. From tyrosine, who is going to come? Melanin. Melanin is going to be derived from tyrosine. Here the wear and tear pigment, very very important guys. Wear and tear pigment are the pigment indicator of free radical injury. For example, you are eating junk food, you are not taking the proper fruits, okay, you are not taking proper vitamin rich foods. So what happens, continuously in your body free radicals are being generated. You are eating junk foods. What these free radicals will do, continuously they are going to act on the cells, they will cause damage to the cells. Now cells are being repaired, so there is something wear and tear, wear and tear continuously. Cells are getting aged. So during this process, certain pigments will accumulate inside the cell, which will give you brown coloration of the cell. Brown color pigment is going to accumulate inside the cell. Do you know what is that wear and tear pigment? The pigment which is a marker of free radical injury. The pigment is called as lipofuscin. Okay, lipofuscin. Okay, lipofuscin or lipochrome. Lipofuscin or lipochrome is seen. Okay, lipofuscin and lipochrome is seen in brown atrophy of the heart and liver. It is seen in, it's a wear and tear pigment. It's going to be seen in all those cells which have undergone the free radical damage, or it's going to be seen in those cells which are aged, older cells. Okay, and also the last one here, the golden yellow pigmentation is seen in, okay, the golden yellow pigmentation is seen uh, in those conditions like bronze diabetes. Okay, bronze diabetes, I will explain to you, don't worry. Bronze diabetes are in hemochromatosis. So what exactly is this hemochromatosis? Already discussed. Hemochromatosis means the patient is having iron overloaded state. Okay, iron is now getting accumulated in the body, lots and lots of iron. The exact reasons of hemochromatosis you'll study in pathology, like in systemic pathology. Okay, this is general pathology, right? Iron overloaded state, iron is accumulating. Now this iron, do you know what it will do? This iron is accumulating in the skin. Okay, it's accumulating in the skin. It causes bronze coloration of the skin. Actually the entire process is different, it will stimulate the melanocytes. The process is different, but try to understand like this. Iron is getting deposited in the skin, sir, which gives the brown discoloration. Okay, that's called as a bronze diabetes. Now why we are using the word diabetes? Why? Because those patients who are suffering with hemochromatosis, this iron will also like to accumulate inside the pancreas. Now this iron, it's a free radical, it will generate free radicals upon reacting with the water. Penton's reaction will happen. Now this iron will kill the beta cells of pancreas so that there is no insulin, leading to diabetes mellitus. So bronze discoloration of the skin, giving the word bronze. Death of the beta cells in the pancreas will give you the word diabetes. Bronze diabetes is seen in hemochromatosis. Now, what is the pigment that is getting accumulated? It's a hemosiderin. Hemosiderin is nothing but the iron. Iron accumulation inside the cell. The iron accumulation inside the cell will give you golden yellow discoloration of the cell. It's due to accumulation of hemosiderin, nothing but iron. So after this also we have discussed about the dystrophic calcification, which is going to be seen in the dead tissues. I have given you the mnemonic most PG, most PG is the example of samoma bodies I have already discussed with you. And also here I have given you the conditions of metastatic calcification in hyperthyroidism, sarcoidosis, renal cell carcinoma, like renal failure. Okay, in milk alkali syndrome, in all these conditions, what you will see is metastatic calcification. Okay guys, with this we have done with the chapter of cellular injury. If you know this much, that's more than enough for you. Okay, so in the next class, tomorrow's class, let's start our new chapter, that is the inflammation. What are the types of inflammation? Acute inflammation, chronic inflammation, the vascular changes of acute inflammation, the cellular changes which will happen in acute inflammation, that we will discuss in that tomorrow's class. Hope the class is helpful. We'll be sharing this entire PPT in the group. Okay guys, thank you. Bye for today.